So it's not the atoms themselves that are fuzzy, it's more of the electron or the electron cloud. This is a kind of more accurate representation of what an atom looks like. You see the nucleus at the center here, and it's surrounded by a cloud of electrons. This electron cloud reflects kind of the probability of where you expect to find an electron around an atom. And so you can see the denser area as more close to the nucleus, that's where you're more likely to find an electron compared to this more lighter area on the outside. So with an electron microscope, what we're imaging is the nucleus using electrons. So there's an electron beam that's fired through your sample, and that beam interacts with the central part of the atom, the nucleus right here. This nucleus can absorb or deflect the electrons, and that will cause a contrast difference between the sample and just the rest of the grid. So going back to the electron microscope image, these nanoparticles are made of lead selenide. So they have a really heavy atom in them, and the heavier the atom, the more protons that atom has, the more it's going to scatter and deflect and absorb energy from the electrons in the electron beam. So you'll get a darker image as compared to the rest of the grid, which is mostly carbon. So you get this kind of light gray image. And we have to use electrons because the diffraction limit is wavelength dependent. So something with a smaller wavelength is going to have a lot smaller diffraction limit than something of a longer wavelength. And since these nanoparticles are really small, we have to use something that has a really small diffraction limit or a really small wavelength, i.e. an electron. Resolution is the ability to kind of distinguish 2 points, and this image behind me kind of describes that. And so you can see on the top one, you can see there's clearly 2 points, but as these points come closer and closer together, they're less easily able to be resolved. And for each of these images are perfectly focused. It's just that the points are at different distances, and at a certain point, at that wavelength, those points are too close together to be able to be resolved. So that's resolution. And there's an equation that describes the resolution of an imaging system, and it's called the Abbe equation. It says that the resolution of your imaging system, D, is related to your wavelength, lambda, divided by the refractive index of the medium between your sample and the source, and the objective factors. There's also a relationship between a particle's wavelength and its mass and velocity. And we can accelerate electrons to really high speeds because when you apply a potential to an electron, the potential field that it's in becomes that electron's velocity. So what you can do is you can, in a TEM, adjust the voltage that's applied to the electrons to get higher and higher resolution. So in an electron microscope, by changing the accelerating voltage, you can get different resolutions. And so for kind of a standard electron microscope, you're using around 200 kilovolts, so 200,000 volts accelerating voltage to get, this kind of resolution. But you can see that as you change some of these factors and the accelerating voltage, you'll be able to see different sizes, or your diffraction limit will change. But yeah, kind of the short version of this is that we can get these images because electrons' wavelengths are significantly smaller than wavelengths of light. And when electrons interact with the nucleus of an atom, they're scattered or deflected, or some of their energy is absorbed. So when they hit the detector, they have less energy and they create a dark spot compared to some of the lighter regions where the electrons kind of pass through more freely, unrestricted. I hope you enjoyed this video. This is Mad Bioengineer signing off.